Just change it.
Situation.
Change it.
You will change it to what?
Yeah.
It's an honor to be here to share with you guys some of the progress I have made on my project titled Transcription Regulation of CFTR by Intestine-Specific Enhancers. So first, I will bring you some of the backgrounds of the disease cystic fibrosis, then I'll tell you the significance of my research. Also, then I will dive into details of the aims and the data. Finally, we'll summarize. So cystic fibrosis is a monogenetic disease. It affects a number of people, 30,000 people in the US, and this disease affects different types of epithelial cells across the body, different organs. For example, in the sweat glands and also lung epithelial cells. The mortality of cystic fibrosis is caused by lung complications, including bacterial infections and lung fibrosis. And my research of interest is focusing on the intestinal epithelial cells, which are involved in the phenotype of Meconium mitis, and which is a obstruction of the intestinal gut when the newborn babies. Also, the chronic intestinal constipations, which are observed in the adult patients. And the cystic fibrosis disease is caused by this large protein, which cystic fibrosis transmembrane conductance regulator. Alteration or mutation in this protein will lead to malfunction of this native function, which is transport chloride ion across the membrane of epithelial cells outside of the membrane. So, alteration of this function will lead to decrease of chloride ions, and water follows the salts. So there will be dehydration of the mucus outside the membrane of the epithelial cells, which lead up to potential bacterial infections, and for example, in intestinal cells will be obstruction of the intestinal duct due to the thickening up of the mucus. There's different kind of mutations affect cystic fibrosis. People have been classified into 5 classes. So shown in here, class 1 is the people who has problem with the transcription or translation process of the protein. There's frame shift mutations and some splice mutations and nonsense mutations. And class 2 mutations, which are the protein trafficking or protein folding mutations. Most famously one is the del508 people, which have allele frequency of about 7%. It's the most common mutations. It affect the protein trafficking in the Golgi. The protein trapped in the Golgi and gets degraded. There's no functional protein in the membrane. And class 3 and class 4 are protein function mutations, which these proteins get trafficked to the correct location in the membrane, but they either cannot open the gating correctly, or they can open, but the transportation of the chloride ion across the protein is malfunction. And the final class of the mutations are less synthesis, or just overall has less functional CFTR on their membrane. The net result is the same, that have not enough CFTR to transport chloride ion, and usually these people have less phenotype, less severe phenotype. And over the last 2 decades, people have been discovered about 2,000 different types of cystic fibrosis associated variants. It's really complicated as shown here. This is a representative of the 47 out of the 312 causal mutations, which have been validated either by clinical data or experimental data. There's a lot of mutations in the exon, and there's a number of mutations in the intronic region as well, first, mainly affect splicing. And shown in this graph is the allele frequency of different kinds of mutations. There's only a few that are common mutations in the front, and as you see, right after all the other 2,000 variants or allele frequencies drop to significant. So here is the significance of my research in potentially helping the cystic fibrosis patient. So my research, or the Harris Lab research, is focusing on the transcription regulation, as shown in this cartoon here. So we have known a lot about the exon mutations and the splice site mutations. What we don't know about is the transcription regulation of CFTR. So, for instance, the enhancers. The regulation of the transcription could be used to utilize to enhance the transcript level of this CFTR, and we can regulate this process upstream of all of the downstream processes in the nucleus. So potentially, we pump more transcript, and then we will help all of the downstream process. So that's, for example, I showed here, the first benefit of my research will be that assisting the treatment of ivacaftor and lumacaftor, which is two small molecules that helps treating the protein trafficking and protein gating mutations. So by providing more transcript, they have more resources to work with and could potentially help the CF patients. And the second point of my benefit to the CF patients is we could, by studying the transcription regulation, we could help the current patients that have no treatment, which is they have no protein but they have functional transcripts. That's about 5% of the people. And also our lab is also involved in active ongoing research to verify some of the new novel enhancer variants that potentially cause cystic fibrosis phenotypes. We're working on this, and then we could use our knowledge in the transcription regulation to help these group of patients as well. So my project's hypothesis is that through the study of transcription regulations, we could identify some method to enhance the transcript levels, and using this to treat different kind of mutation of CF. So the aim one here is building on the previous decade of research. We hypothesized, or we aim to discover this enhancer corporations. There's two enhancers in the CFTR regions that are potentially cooperating together. We want to test this in the intestinal epithelial cell. And the second aim is using all of the existing knowledge in the epithelial cells to translate this knowledge into real human organoid to test if we can potentially treat a few types of CF mutations in the human organoid by enhancer activation. So this is a slide that shows here that is DNA representative chip data that shows the open chromatin tracks. Here is the skin fibroblasts, primary tracheal cells, bronchial cells, and the table to represent the intestinal cancer cell line. HT29 is also intestinal colon cancer cell line. And the primary epididymis. So skin fibroblast does not express CFTR, and all of these express some amount of CFTR, as shown